Okay, good morning, good afternoon, good evening, depending on where you're joining us in the world. Welcome to the MechE Alliance seminars, day 13 or 14, I've lost count now. So it's our weekly connection to the world in this COVID era, but also allows us to engage with the students, the faculty, and our external partners across the department and across MIT. My name is Brian Anthony, along with Teresa Worth and Irina will be your hosts for today. I'd like to introduce Professor Mingda Li, who is a professor at MIT in nuclear science and engineering. He completed his bachelor's in Tsinghua, and also sort of connection close to home. He did his postdoc at MIT in mechanical engineering with Professor Chen and the late Millie Dresselhaus. So today he'll be graciously sharing his time and his experience and expertise in sharing his work on a tale of two singularities, or exotic phenomena and energy applications induced by topological singularities. So please hold your questions to the end. You can raise your hand or chat. And with that, Professor Li, I turn it over to you, and I look forward to hearing about your exciting work.
Thank you, Brian, for a very nice introduction. Hello, everyone. It's been a really great pleasure today to give this presentation. So today, the topic is about topological materials. So in the past decade, as we probably see, various types of topological materials, they have attracted vast research and industrial attention for a number of reasons, such as like the electronic and spintronic device without any dissipation, so even better than superconductor. Or there are also some fault-tolerant quantum computing device applications. So today is a presentation about one specific type of topological material. So this discovered about 4 or 5 years ago, called a Weyl semimetal. So this term is because this Weyl, as a mathematician, so he found out these solutions to the Dirac equation, and that's some like light particles in the material. And the singularity is the essence of the Weyl semimetal, which we'll introduce very shortly. And the two singularities, because all these singularities come in pairs. So for today's presentation, I will first give a very short introduction, linking the topology and directly to the topological Weyl semimetal. So what is a topology and how they are actually linked to the Weyl semimetal. And I will provide 2 examples from our recent work. So one is the more fundamental. So if it's the topology from electronic degree of freedom, so how can we visualize the topological effect from like an ionic degree of freedom? And it's not some higher order small effect, but see it in a very definitive way. And the last one is another application, also using the singularity to do thermoelectric energy harvest. So to begin with, so what is topology? So a very common example which people like to give is like using this cup, and it has this hole and in this handle, and after some continuous shape deformation, eventually it becomes topologically equivalent to a donut. So that is become very common example. But today I'd like to provide another example. Actually, you will see it's directly linked to the essence to derive a Weyl semimetal. So this example is a question to ask: why the human hair, there is almost always one vortex, and it's called a hair tool. So like this vortex on the head. So to address this question, let me give a few this background. So this is topology in the 2D smooth manifold 2D surface. So in the 1D, if we have a surface, or we have any curve, and we can define a quantity called a curvature. So if in the local area, it's tangent to this circle with radius r, then the curvature is just 1 over r. So for a 2-dimensional surface, the definition is similar. So people can find 2 orthogonal, call it prime, these directions, and at each direction, they can define its corresponding curvature as a curve. And then from there, we can further define the Gaussian curvature. It's just the product between these two curvatures. So for example, if we have this saddle shape, and one shape we have like this circle shape, then 1 over r, but the other shape, it may be a different this curvature. And if we have a cylinder, we want to define curvature, because even one direction we have a circle, the other is just a straight line, then curvature is 0. And the most relevant example is a sphere. Sphere, we pick up two orthogonal directions on the spherical surface, and each direction is 1 over r. So that's the Gaussian curvature is 1 over r squared. So what happens next? So by defining the Gaussian curvature, so we can define a total quantity by integrating over the entire surface S. So that is called this Euler characteristic. At most, we can do a normalization 1 over 2 pi. And as a result, this total, this integration is, later we see, it's a topological invariant. And just like the number of holes, it will stay constant by changing from a cup to a donut. And here, if we have different shapes, this total chi, this Euler characteristic is also a constant. In particular, because we know for a sphere, the Gaussian curvature is 1 over r squared, and after integrating over all these spheres, 4 pi r squared, and we divide by 2 pi, we get this total chi is 2. And why this is important? Because the physical meaning of this Euler characteristic chi, it denotes the total number of singularities on the surface. So now we can look back to the example on this like a human hair problem. So if we imagine like this hair like some vector field growing on the sphere, and from this Euler characteristic, we know the sphere has the chi equals to 2. So that means it's like 2 singularities on the whole sphere. So in a physical related example, if we imagine we really have a magnetic monopole, and at the North Pole and the South Pole, the vector field will also have singularities. So why the person have one? So roughly we know the head is roughly a hemisphere instead of a full sphere. So it just has one singularity. And that's the consequence of topology. And the more interesting factor from here is that, so this topological effect is very, very robust. So that leads to almost everyone has like one hair tool, and even you see someone may have 3, and then there are 2 of them should be like left-handed and right-handed, which they cancel out each other. But the thing here is actually share exactly the same mathematical correspondence to what happens to a topological Weyl semimetal. So here is a slightly transition before we formally introduce the Weyl semimetal. And so here is its introduction. We have a few things. First, to define the topology, we need something called a curvature, and we need some topological invariant, in this example called the Euler characteristic, and we also need a field. Here is the human hair as a vector field. And then how does this example translate to topological Weyl semimetal? So the first thing, we need some space. So for the hair tool topology example, so this is some kind of closed surface, like the head or the 2-dimensional manifold. It's in real space, or we call it R space. And to define topological material, here are 2 different examples, and this are called like a quantum Hall insulator, which is more commonly introduced, and this is a newer topological Weyl semimetal. So for like a quantum Hall effect, or they call topological insulator, so the space, instead of 2-dimensional space in real space, it becomes in reciprocal K space. And the same thing happens. It's not the full Braden zone in K space, but it's become a closed sphere in K space. And just like we define a quantity of Gaussian curvature, and in these topological materials, from their wave function, so people can define another quantity called the Berry curvature, play the same role as Gaussian curvature in real space. And also, just like a topological invariant of Euler characteristic, the Chen number defines the topological this quantum Hall effect. If we have seen different quantum Hall plateau, n equals to 1, 2, 3, 4, they are all different Chen numbers. And here, for the Weyl semimetal, if we integrate a closed surface in momentum K-space, we get another quantity like Euler characteristic, but we can call it a chirality. And mathematically, these three have also very same formula. It's just the integration of the curvature over a closed surface, either in real space or momentum space. And as a result, the Weyl semimetal we can derive. So the Weyl semimetal is like a linear dispersive, light-like fermion, and has two Weyl nodes. The two Weyl nodes has opposite chirality. You can consider like a light has left-hand polarized and right-hand polarized this light, and here these fermions are polarized. And they are all separated, not in real space, but in momentum space. There are a few different examples showing why the Weyl semimetal is interesting. So for example, the chiral anomaly is fundamental like CP symmetry breaking, and the charge, this chiral can be non-symmetric, and when the B field and E field are parallel to each other, or there are some very interesting topologically protected surface state called the Fermi arc, not everywhere, but only in arc-shaped space in momentum space. And there are also some Berry curvature singularity can induce the giant thermoelectric energy harvest. But in order to determine topology, so many experimental methods, such as RPES, angular resolved photo emission, they have very high technical barrier, requiring high vacuum, and only can detect like surface cleavable these materials. So the number of materials are also limited. Then the question we can ask, so this is the RPES setup, and so this is a typical approach. They need to do ab initio calculation to compute this band structure. This linear dispersion is from the Weyl fermion and compared to the experiments. And here are the few limitations. So from there, so one question we can ask, can we really detect this electronic topology from ionic or lattice degree of freedom? Because we know electrons and ions are two basic elements of any atom. And so to answer this question, a very straightforward idea, because we know electrons are coupled to the ions through this electron phonon coupling effect. But these electron phonon coupling effects are usually very weak. So there are many examples when people try to study electron phonon coupling, such as the phonon can limit the carrier mobility and in the semiconductor, or let's drive the BCS superconductivity. But there is one exception which can make the electron phonon coupling strong. Not normally strong, but strong even in a divergent way if it fits a special condition. So that is called the Kohn anomaly. So Walter Kohn is a physicist. He won this Nobel Prize because he developed this density functional theory. But this is another discovery he made. So what he said, if the electron with momentum K1 scatter with a phonon Q, and certainly on the Fermi surface, it becomes another electron with different wave vector K2. When the K1 and K2 parallel to each other, so the capability of the electrons that can screen this lattice, because the electron is negatively charged, lattice are positively charged, the screening capability will have a very sharp change, and that will make the dielectric function derivative divergent. And eventually that results to an observable phonon softening. And even it is not so sharp from the phonon spectra, but if we can consider electron phonon coupling constant is only order of 0.01, and in the normal perspective we square it, so only 1 in the 10^3, so this is still kind of large effect in that situation. The Fermi surface, on the other hand, only exists in metals. So for our case, So we don't have the Fermi surface like a Fermi liquid in the metal, but we have this paired topological singularity, which we can call it the Weyl nodes. Can we induce Kohn anomaly in the Weyl semimetal? So in our recent work, we showed theoretically and experimentally the answer is yes. So led by 4 of our group members, Tan, Fei, Nina, and Ricardo. So the first thing we wanted to do is to provide a theoretical prediction to show, in principle, Kohn anomaly can actually happen. So that's done by Nina and Ricardo. So we carried out quantum field theoretical calculation. So this is this electron polarization operator, so showing how strong the electron can screening this phonon energies. And then based on this calculation, we provide a criteria where we can expect a Kohn anomaly. So the left figure here is this conventional metal. We know when the 2 electrons, the wave vector are parallel to each other, there will be Kohn anomaly. Here we show if we have 2 Weyl nodes, we can call it located at KW1 and KW2 in momentum space. And if there is a phonon, link these 2 Weyl nodes with wave vector Q. And if they also matches the energy difference between the energy of the 2 Weyl nodes, mu1 and mu2, affected by the phonon energy omega, then that's where we can expect a Kohn anomaly. So that is predicted by pure theory. The theory also predicts a few other features. So for example, comparing to conventional Kohn anomaly, there is a chirality selection rule. That means the 2 Weyl nodes, the singularity must have the same chirality, right polarized to right polarized, in order to let that happen. If they break the chirality conservation, it's not going to happen. There is a strong power law divergence, and we can even compute the phonon softening profile in momentum space, what kind of shape we would expect. And after this theoretical part, so we came to this experimental planning stage. So the materials we choose, we try to demonstrate this effect is TAP, tantalum phosphide. So the reason is that it has a very clean 2 sets of the Weyl nodes. So up to date, people call the material the only one type of Weyl nodes are ideal Weyl semimetal, and that hasn't been existed. And for the TAP, the 2 sets like W1 and W2 is already as cleanest as we can get. And then our lab, we synthesized the crystal by Fei, Tan, and Nina. So prepare this material to grow it as large as possible for the inelastic neutron scattering measurement, centimeter size, and also down to micrometer size for the inelastic X-ray scattering measurement. And one specific prediction from theory, because this material also has an interesting feature. If we have the KW1 Weyl nodes scattered to KW2 Weyl nodes, the phonon Q wave vector is another KW2 Weyl point. So at any KW2 Weyl nodes, we expect a Kohn anomaly to happen, but not a KW1, which we explained a lot of detail in the paper why that's the case. And we also provide this density functional perturbation theory, showing at high symmetry lines, this theory, DSPT calculation, and measurement are in general good agreement. And now we come to this main measurement. So if we have this Weyl fermion from KW1 scattered into KW2, if we have a phonon at Q, which we can call it located at KW2 prime, and then we expect a phonon softening. So that is the raw data without any processing. As we can see, located at this Weyl node, there is a softening exist. And we can also show this softening appeared at low temperature and room temperature, and comparing with the density functional calculation. And we can see the calculation shows it's a flat band and without considering electron phonon coupling. But here we saw that apparent phonon softening, which also agrees with the theoretical prediction, this bowl-shaped softening. And agreement between observation and the theory is actually met in a very high precision, less than 1% error. And comparing to this KW2 Weyl node, which we expect Kohn anomaly to happen, if we go to another Weyl node, like a W1 shape, so although there seem to be also scattering channel from a KW2 to another KW2. It can scatter into a KW1 Weyl node. So we didn't expect the Kohn anomaly to happen, as observed is also flat band, and our initial calculation agrees well with these data points. And the reason which we believe is from the chirality selection, because in order to let this to happen, in addition to momentum conservation, it has to satisfy the chirality conservation rule. But all these Weyl nodes, whenever they satisfy momentum conservation, they will have to have opposite chirality. So the Kohn anomaly in KW1 will not actually going to happen. So there are actually a few these applications that can be used from this kind of the measurement. So the first thing is to directly measure the electron-phonon interaction strength. That's basically how soft it is. We can extract that directly. So why that's something we think is important, because for many low temperature topological phenomena, at a higher temperature, there are more phonons, there are more inelastic scattering that can actually gradually break the topological protection. So if we know that materials and they have very weak electron-phonon this coupling, and then that is good for the room temperature device applications. That's also one reason why this quantum computing device has to be run at extremely low temperature, because they want to be immune from the phonon scattering. And another more non-conventional application, which people already nailed the term chiroelectronics from other studies, but because in our current case, there is a strong chirality selection, and we can select to let only one this Weyl fermion with definitive chirality to dominate the transport in these electronic properties. And that can be used as chirality dependent electronics. And this is a more fundamental example. Are there any more practical application using the topological singularities? So one example today I'd like to introduce is on thermoelectrics. As we know, the thermoelectrics are characterized by the GT, the figure of merit, and a significant effort has been spent on reducing thermal conductivity to make them separate from the transport of the electrical conductivity, make the K as lower as possible, but try to maintain sigma as high as possible. But actually, at the square sigma, the product, which is called the power factor, has some kind of upper limit. So here is why. So for metals, so for example, although so we have a very large carrier density, so many high conductivity. Actually, the entropy, which is related to the feedback coefficient, the thermal power, is very small. So that's why metal almost never good as thermoelectric materials. So contrary to that, for the this semiconductors, there is a trade-off between electrical conductivity and also feedback coefficient. At a higher and higher doping level of say this carrier density, there will be the reduce of the feedback coefficient because the reduce of entropy, but then the sigma will also increase. Then the product at square sigma has some kind of optimized value on the order of 1. And so there's the recent predictions, which is done by the MIT physics professor Liang Fu and his group members, shows that the Weyl semimetal has a special feature which may break the upper limit of this power factor. So for one thing, for the feedback coefficient, if we apply a magnetic field, it can keep growing linearly without a saturation. But most importantly, how to do this sigma in a conventional material. When we have a high magnetic field, the electrons will experience this orbital cyclotron motion gradually localized in real space. But for Weyl semimetal, because this topological singularity is protected, it will remain without a gap opening. So all the electrons near this Weyl point will keep flowing, and which maintains high electrical conductivity. So that's following that prediction, we carried out this measurement, like on the longitudinal feedback coefficient. and that's reached to a very high value at about 40 Kelvin, over 1,000 microvolt per Kelvin. And comparing to that, so the highest lies in the power factor. So if we look at the conventional non-topological, like a semi-metal, like a bismuth, they can still reach very high feedback coefficient under magnetic field, but the price to pay is to make it a very high resistance. And here, because of this topological protection, which can maintain the high electrical conductivity, so the resulted power factor, and it can be 2 orders of magnitude higher than non-topological semi-metal. And this value is actually very big, order of magnitude in many typical this thermoelectric material, like a lead telluride and bismuth telluride. And so that's, we have other theory to explain why this is the case. From the topological protection from this paired Weyl nodes. So as a brief summary for today, we introduced this topological singularities in the Weyl semi-metal, and that's the Weyl nodes. And in a different context, the topological singularity can mean very different things, like the Dirac monopole or even the dislocation in the crystalline solid. They are all some singularities. And the Weyl nodes, today's this paired topological singularity, they are intrinsically magnetic monopoles in the momentum space, and they are all paired. And from there, we can use that singularity to induce a new class with the Kohn anomaly, with some chirality selection rule. And also there's some dynamical effect because the phonon energy need to come into play to assist the transition to happen. And also there's strong power law divergence, but that's, we won't be able to verify that from inelastic scattering measurements. And another more practical energy application, and which we learned, I think the take-home message, even it's not shown from this data. So what the ultimate thermoelectric may look like. So what I can say from this high magnitude of the data, so an ultimate thermoelectric material, it may be a magnetic Weyl semi-metal, and because then we don't need to apply external magnetic fields, and the Fermi level lies at this singularity of the Weyl nodes, and then it can generate a really very large this conductivity, and also maintain very high feedback coefficient at the same time, breaking this barrier of the power factor. So I think with that, I will stop here, and really to thank all my group members and collaborators, and also thank you for all your audience for the attention.
Mingda, thank you very much. I sent you the virtual and the physical clapping, so thank you. So
thank you.
Participants, please, if you can raise your hand or ask questions. Let me just kick one off quickly. I as a comment, I love the fact that you started with the hair swirl and sort of connected to topology of that, and sort of have applications and interesting energy harvesting applications. But let me, actually, I'll just ask Marius's question here. Why were Weyl semimetals found only 5 years ago? But what was the breakthrough necessary to bring this out into the light?
Wow, yeah, that's a great question, and I feel there are certainly a number of different reasons, and so the topology, they may start at the beginning in 1980s, so that's at a quantum Hall effect, but back then, it's mainly focusing on this topological effect, the Chen number, but not trying to find so many materials realization. So that's about 2005, 2006, that people brought up to this going beyond the quantum Hall insulator, which is like a quantum spin Hall insulator, also called a 2D topological insulator. So that's more natural to be comparing to like the 1980s quantum Hall effect, because everything they are filled up and in the two-dimensional beryllium zone in K space, and they have very well defined Chen number. And so only after this discovery of topological insulator, with all the field band gap for a few years, people started to realize, okay, the topology can also be introduced not only in insulators, like a trivial and topological insulator, but also in metals. And that's a conceptual breakthrough. And even though we currently see all these this comparison become simple, it still took really serious time to get there. And the other thing is the Weyl equation has been there for like 90 years, but it's really hard to find like a real material realization. People were considering like a neutrino from high energy physics, and only like 2015, and that's the time when people predicted by the density functional the theory showing real material and can really host this kind of the exotic Weyl fermions in solid state system.
Very nice, thank you. We have some questions in chat, but I know Nick Fang has his hand raised. So Teresa, if you can let Nick ask his question.
Yes, Professor Fang, you should be able to unmute and ask your question.
Great, thank you very much. Really appreciate. Yeah, this question is for Mingda. How would you elaborate the perspective of chirotronics? Say devices that leverage on chiral transport of different electrons, and in your opinion, how this will differ from existing effort, or so to speak, perspective of spintronics?
Yes, very good point. So I'd like to mention two things. So one, so this chirality dependent transport has been demonstrated, partly related to Professor Newgatic group in MIT physics department, but they used optics. So imagine if they use like a left-hand polarized or right-hand polarized light to shine on the Weyl semimetal, then the resulted transport. You can consider the carriers can be transported even in the opposite direction, physical direction. But here, from this our work, because the electron phonon interaction is also chirality dependent in this case, so this can be achieved without using light. So that's the one thing, without using light shining on it, but naturally through the electron phonon coupling. And the other thing I think is very interesting related to spintronics. So I think this term is still very rare, but it appeared in literature in the past 2 years. And when we talk about spintronics, it's mainly related to some like this 3,5 or 2,6 semiconductor, and they are like a parabolic band, so non-relativistic these electrons. And even for non-relativistic electrons, and only at zero velocity limit, the spin is a good quantum number. And in that point, the spin is perpendicular to the motion of the carrier. So if electron move to the right, and the spin may be pointing to the up. And here the chirality is another limit. So it's the ultra-relativistic limit. The chirality is like the vector, but it will point either parallel or anti-parallel to the this motion direction of this Weyl fermion. And one natural advantage is that so the light couples spin not in a very natural way, but the light has the like a left-hand polar and right polar directly coupled with chirality. So that means if we are thinking still considering some optoelectronic device coupling with light, I say if they can really build a good chiraltronic device, that may have some advantage over spintronics in that context.
Great, thank you very much.
Thank you. And maybe related to that, let me take a question out of order here from Matthias as well. Why do the nodes that exchange energy have to have the same chirality? What forces this selection rule?
Okay, yes. So you can consider there are some discrete symmetry here, and phonon itself, it does not carry any chirality. So the just like any time reversal symmetry or other like inversion symmetry, So here, if the interaction won't break the symmetry, you can consider that in spintronics, there is no reason to put a spin up electron become spin down unless they hit some magnetic impurity, because magnetic impurity breaks that symmetry. Here, the interaction of phonon do not break the chirality, and also there's no driving force to switch the chirality.
Marius has his hand up, Teresa. Marius, can we take him off of mute? And if I didn't ask the complete question, Marius, please add.
Yeah, Brian, you asked him perfectly the question. Thank you. I just raised my hand because I also want to ask a simplistic or maybe stupid question. So I didn't dare to write it down in chat. I'll just ask it orally. Mingda, great talk, by the way. You really stretched my brain on this one. The question I want to ask is, when you talk about phonon softening, does it imply that's an inelastic effect, or is this all elastic scattering? And what does softening mean in that context?
Oh, the softening means it's the phonon dispersion, or we can say phonon energy in momentum space. And it's softened at a specific location in momentum space where Kohn anomaly can happen. So if without this data, I can show you this is another example, and on a metal lead. And there is some observable softening here, and at a very specific Q value, which is when Q phonon wave vector equals to twice of this electron wave number Kf. So at a specific K value, the phonon energy just reduced, lowered. So that's the meaning of a softening.
Oh, cool. Thank you.
Thank you.
Thank you. Vivishek has his hand up, so let's go to Vivishek.
Yeah, so how do you know that there are no intranode interactions here? Are you able to perform any highly resolved studies of phonon scattering or things like that that might shed light on this question?
Yes, so it's a very good question. So I think it's different from the question you put on the question panel, but I will ask one after one. So in this particular material, if we look at the softening condition, and it only happens at a specific Q, and gradually the softening will disappear and away from that single momentum value. And then from the measurement, it has a very high momentum resolution. So we can put all the arms of the setup and detector to just detect the phonon at that specific Q value to see the softening and know that effect is true, and slightly move away from it.
Thanks.
So let me ask the following two questions as the last ones to respect people's time and at the quarter hour. Both Vivishek and Adela are asking questions. I'll characterize them as related to characterization or experimental techniques. So the first question, are you able to resolve, perhaps by optical phonon scattering, whether there exists any intranode interactions? And then the second question is, what are some of the state-of-the-art techniques in experimental characterization, whether it be inelastic X-ray, neutron scattering, et cetera?
Yes, very good question. Let me answer one by one. So there are always a lot of intranode scattering interaction, but we can consider if we only have the intranode and this Q value will be at this zone center, which means the Q value is not like away from like maybe just a pi over A and at that regime. So in the work, we showed the data and some softening from that data. And but there is some also, we don't have to use this method to measure zone center. We can even use Raman scattering, which we also showed some data to measure optical phonon, which becomes more apparent. And the other thing, I saw another question, I thought that's related to measurements. So these inelastic scattering are instrumental to the research in my group. And so we mainly do this in the DOE a few national labs and combining this X-ray and neutron techniques. And I think the last one from Mingda Li is
So the question,
Yeah.
so everybody hears it, are transport applications using WSE bound to scattering effects at the surface that may hinder performances, or do the exotic surface behaviors mitigate that classical limitation in some way?
Yes, I think it's a very good question. It will, so for the energy application, it does not help too much because the sample we were using is really a bulk, a single crystal, and like 1 centimeter long and like 200 micron thick. In that situation, the surface state, which only will diminish after like 2 nanometers, and that will going to contribute to this transport. But assuming it's not this particular example, but you are talking about some thin film growing by MBE, and then people have demonstrated that this surface scattering can become dominant. And in that case, because these two singularity, and in the middle, it has a finite Chen number, it's actually topological protected, and this carrier from the surface state of Fermi arc have very high mobility, which can be also used to build like a high-speed electronics.
Very good. Mingda, thank you very much for the phenomenal work and your time and the presentation. And attendees, participants, please, thank you very much for all of your wonderful questions and the dialogue. That was quite pleasing to experience. So again, thank you, the physical and the virtual clap. As everybody knows, this is our weekly seminar to engage with the community. Next week, we'll have, from mechanical engineering, Professor Isaac Ben Henry, speaking about his work, looking at heat transfer at the atomic level, and on developing technologies that can help mitigate climate change. So please join us next week, same time, same channel, Wednesday, July 29th at 12 noon. Until then, Mingda, again, thank you very much. And
thank you, Brian. Thank you, everyone.
Thank you, Professor Li. Thanks, everyone, for joining.
Everybody
thank
stay
you,
safe.
Teresa.
Have a good day.
Thank you.
Oh, and I guess Teresa reminded me that the last thing is as we want to engage the community that people would like to hear from. So whether you want to self-nominate or recommend colleagues in the department, out of the department, out of MIT, please send us a note. And we look forward to inviting others to participate in our weekly conversation. So again, thank you.
Have a good day, all. Thank you.
Thank you.